Hi, my name is Jose, and this is my Physics 2 Lab 4. A little bit of an introduction. The purpose of this lab is to measure the magnetic field of a small bar magnet at varying distances. A little bit of preview of results. We got that n was minus 1.5561, and then the magnetic dipole moment was that big number down there. So some of the physics principles and models that we'll be using in this lab is the Biot-Savart law, which relates a magnetic field at a point to a tiny current element, which is, as you can see, that's the equation down there. And then the magnetic field of a dipole is when a magnetic dipole is in closed circulation of an electric current system, and it's that equation right there. And then the distance dependence formula is the magnitude of the magnetic field due to a bar magnet decreases as the distance to the magnet increases, and it's those two formulas down there. Magnetometer. For the experiment, first I positioned the magnetometer perpendicular to the Earth's magnetic field. Then I found the location of the magnetometer, which is marked by that red X. Then I measured the magnetic field at the magnetometer when it was moved closer and farther away, and on and off axis from the bar. So in this case, the D perp would be changing for on axis, and then for the off axis, it would be changing like in the picture on the right. And the system is the bar magnet and the magnetometer, and the rest is the surroundings. So some data analysis for the on-axis part. This best fit line models the equation that we saw like on the previous slides. So this means, so based off of that, we can determine that n is equal to minus 1.5561 and the ln of k equals 0.9917. And that's a picture of my data right there. So I had to do some calculations to find mu, the magnetic dipole moment. So since we knew ln of k, we can find k by doing e to ln of k. So we did e to the 0.9917, which equals 2.696. And rearranging the equation and solving it out, we get the big number down there, which is our magnetic dipole moment that we calculated with our experimental data. So this is all the data we got for the off-axis part of the lab. And specifically from this part, we'll be focusing on using the deep perp part of this data, the average specifically. So now going into the code, now gathering all the data from our experiment, we plugged in of the magnetic dipole moment right there. We made it defined a function so we could calculate the dipole V given a mu and an r. This is these, and then this is basically just rinse and repeat with all of these. For some of them were on, these were for the on axis, and then this was for the off axis, and it's just calculating all the different thingies. And then down here is when we calculated when it was at 45 degrees. And yeah, and then this is where we inserted the perp from the previous slide. About it for the code we have. And here on this next slide we have the output of the code that we had on the previous slide. And this helps us visualize everything that's going on with regards to the magnetic fields and everything with the bar magnet and such. Sources of error here. We assume that the magnet acts as a magnetic dipole and that the magnetic field decreases as distance increases. And then other magnetic objects in the area could have affected the readings of the magnetometer, and the location of the magnetometer might not have been found exactly. So some of our observations in this lab, the ones that turned out to be true that we saw was when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. That was true. And then as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases, which is also true. Then we move on to the what if questions. So basically, what if we had an oriented magnetic north how would that have affected our results? So the Earth's magnetic field would have messed with the bar magnet's magnetic fields, which would skew our results. And then the second what if question is if you had two sticks that are identical magnets together end to end on the experiment again, how would the results differ? The magnitude of the magnetic field would double, but the direction would stay the same.